Hello and welcome everyone. I know it's been a while, but I am back. At least I am today, and we'll be discussing the James Webb Space Telescope because who doesn't love astronomy? Well, I certainly do. I hope you guys are looking forward to some nice physics about what we're looking for and what these photos might mean for us in the long term. Does it tell us much about our place in the universe? I'm sure they will, but we will get into that. But first, I can't do this alone, so nice hello to my co-host Jen. Thanks for coming back.
Hi.
Sorry everyone, I know it has been a little while, but I have been busy because I am trying to actually make my title, sorry, wrong end because the camera is mirrored. Not just almost, I'm trying to get rid of that bit of it, and unfortunately that takes a bit of work, and it's been busy, so that is why. Though I do have a few things planned.
When you finish your degree, Matt, are we just going to call you a doctor?
This channel will cease to exist when I finish the degree. My plan is that I will actually just get rid of it and I will start again with a new channel where I take all the lessons from this one and I'll try to do it from a more professional thing based on all of the stuff I've learnt. But I will probably not disappear, but this channel will, I won't delete it, but it will stop being functional, if that makes sense. That's the plan. But that's down the line. That's going to be a little while yet. I've still got a bit to go. So before we get into the actual content today, I just want to say welcome to everybody who is watching. I can see a few people. Sandy, Claire. Oh, we got Hive Science. Hello. And of course, Mark Caesar there. So if anyone else is lurking in the background, welcome and hello as well. Now, the lineup I've got today is I've got a few of the early images. They've got them from NASA. I've got them lined up as a nice.
I like early because early's only a few months old, but
yes, I know, but they were some of the first ones to be unveiled. There's been a couple more, but these are the ones I've actually had a chance to have a look at. And we're going to chat about them. I'll go through, explain how we got them, what you're actually looking at. Because, as we'll see later, none of them are real colors. They're not actually what we can see with our eyes, even if we could pick up the faint amount of light coming from there. We'll get to that, as I mentioned. And then after that, and actually through it, feel free to ask questions. Obviously, I don't have super chat, so if you want to ask me a question, make sure you tag me. And if for some reason I'm missing it, just keep tagging me, and eventually I'll see your question in the chat. We'll get to it. Is there anything you want to say first, Jen, before we get into it, or shall we just go straight to?
No, I think the bit that's going to pass, the bit that I'm really interested in getting to is why astrophotography is never in real color. But we're going to get to that later, and that's going to be interesting, especially with your background, Matt, because it really is kind of your field. I mean, astronomy is not your field, but the colors and light and stuff is your field. So,
I am technically part of an astrophotonics group. The acronym for my lab has astrophotonics in it, because optics. The spectroscopy is light matter interactions, and if you want to know what's going on elsewhere in the universe, well, it's a useful tool to have. And it's one of the few things in astronomy where you can be absolutely precise with it. Background noise and distances ignored, that is. But it is a very, very easy one. But if you're happy, let's...
But we're getting there.
Yes, hopefully this will work. I have some nice images lined up. This is probably the one everyone is familiar with. This one here. Now, the cosmic cliffs. Now, for scale, this picture that we're looking at here is 16 light years across.
And I'm going to apologize for the dog barking in the background, but I can't make him shut up.
Yeah, I was trying to record videos for work yesterday, or voiceovers for them, and the dog decided it was going to whine because I had to keep her next to me. So I get that. And back to where I was, 16 light years across. To give you an idea of how big our solar system is, from the sun to Pluto, depending on where it is in its orbit, because it is elliptical, the distance is not always the same, takes about 4 hours. So 4 to 6 hours. So at most, our solar system, if you ignore the Oort cloud, is about 12 light hours across. We're looking at 16 years here. This is a relatively small section of the sky too, but it's that far away that everything is huge.
I mean, another aspect to that is where we are in our part of the galaxy. We are fairly distant from other stars, but within 16 light years, there's about 30 or 40 other stars that are around us. So 30 or 40 other solar systems would easily fit within that. But this is a stellar nursery, so there's a lot more solar systems than that within that area.
Yes, and that's actually getting very close to what this image is. Now,
yeah.
The actual pillars there that you can see, there's a few columns that are sticking up, a few points there. Those are about 4 light years tall. But what you can see here is, as Jen mentioned, a stellar nursery. And that is where stars are born. That is where you create, or where the universe creates new stars. This is a massive dust cloud. And it's not going to be even because our universe is not perfectly uniform or homogeneous, which means some areas are a bit more dense than others. And when you have a little bit more density, you're going to have a bit more gravity. So that then starts to pull more towards it, and then more. And as more falls in, it keeps going. And eventually, you'll, at least in a few occasions, because it sometimes fails, but you'll get enough density to start fusion, and you end up with a star. And you can actually see a lot, the stars, some of these are quite obvious here. They start to ignite. After a while, and this is the difference if you look at the ones that are a bit above the nursery, a bit above the brown kind of dust cloud, you'll see that once they get going, the UV radiation that they start putting out blasts away that dust and clears it. So it is basically a stellar nursery. The stars are made, and then they clear the actual rest of the debris around them, and you end up with nice new solar systems. The weird aberrations you can see on the brightest stars there, see if you get that cross section, that's not real. That's actually diffraction through, I believe it's through the lens, but that's not what the stars actually look like.
It's a form of chromatic aberration, isn't it?
Sorry?
It's a form of chromatic aberration.
Yeah, I think that's it. I should have looked at that one a little bit more. But the other thing too that is to note here, and there are 2 versions of this photo. I've only got this one here because it shows everything we need. But the other thing is, this is not the real color. This one we're looking at here are wavelengths of light that the human eye cannot see. Because James Webb is not a visual telescope. It's not looking or taking photos for anything that we would see with our own eyes. It's an infrared telescope, which is actually the colors that I tend to use for my PhD or my lasers for that. It is actually quite useful in astronomy to do things well outside the visible, because the visible is such a small region of the electromagnetic spectrum.
The one that gets blocked so easily, which makes it really hard to see things, because there's a lot of dust in space. We tend to think of space as empty, but space isn't empty. It's even in its most vacuumy point, there is still dust. There are still bits of other things, and in areas like this, there's so much dust you can't see through it. But if you go to shorter wavelengths, like that infrared and that, you've got a chance of penetrating, of seeing what's behind the dust cloud, which is very, very handy when you're doing astronomy.
Yes, and that's actually the reason we can see half of the stars through this dust, is that when you move into the infrareds, you're going beyond the red end, you're going a bit lower energy, but if you so this is not the thermal section of the infrared. A lot of the times when you hear about infrared, people think about heat, like the old heat lamps. That you have to go even further into the infrared before you'll get to that one. The images from James Webb are near infrared and mid infrared, and near, as the name suggests, is just near the red part of the spectrum. So that's just beyond what our eyes can see. I think this one is the near infrared version of that. I will double check at some point. Then you can also see for this one, there is the mid-infrared one. And because you've gone a little longer, you can actually see through the dust better. And it looks like someone has put a filter over the dust cloud to remove it. And again, as Jen, you were saying, which is a very, very useful point to note, is that it is good for seeing through the dust. And I do have one of the later pics where you can see just how effective changing that wavelength is. So all you're doing is changing color, but in parts of the spectrum you can't see with the human eye.
It's also interesting to remember that when we design the design of the optics is done for these telescopes, the CCDs, which is the charge couplers that do the light detection in the devices, inside the devices, the same thing that works in your digital cameras, even on your mobile phones, etc. Although these are a lot more precise because they have to be to get the amount of light into them. They are only black and white. They just detect differences in the amount of light that's being allowed in. They get these different amounts of frequencies and stuff like that by putting filters over them. So they make really, really smart filters that actually take down only a really, really short, narrow bandwidth of light is allowed through. And that's the only light that gets on the CCD. And that's not much light. But when you're dealing with something that's so far away, it has so little light that's getting to us in the first place, and then we're filtering out most of that light to just get the wavelengths we want, we're getting even less light. That's why these exposures are so long and why they're really hard to do here on Earth.
Yeah, we're talking, for pretty much all the photos that we'll go through today, we're talking days to get the image. The exposure time is in days. That's how long it
takes to collect that many photons. To do it on Earth is really hard because the Earth is spinning. So you can't constantly for days on end point at one area. You'd have to do it over multiple nights. And then, of course, you've got the atmosphere in the way, which changes the way the photons move, or you end up with clouds in the way that might actually stop some of the light getting through. Astronomy on Earth is complicated and really hard to get any of these really distant, glorious images that we can get in space, which is why you can do better astronomy in space with smaller telescopes. To get the same effect on Earth as the James Webb can get in space, you'd have to build a telescope about 40 times the size to capture the same amount of light. And economies of scale don't make it worthwhile.
There is also another issue if you try and build it on Earth. You have to deal with our atmosphere, which distorts everything. And correcting for that is possible, but it is definitely not easy, and we're still working on getting it to actually be completely effective. But you should see there are some images where they've got, it's known as adaptive optics, where you actually have a mirror that you bend as the atmosphere distorts the light to correct for it.
They're made out of little the mirrors themselves are made out of little hexagonal plates. Once upon a time, all mirrors in telescopes were one big mirror.
I've seen them. I've seen some like that, and I've seen them, the facilities that make them. To get them so smooth, they used to put them in a vacuum chamber and vaporize silver or aluminium, depending on what they want, and you'd actually gas coat. It was a crazy way to make a mirror.
Yeah. Oh yeah, but the modern ones are all just smaller hexagonals that actually fit in together, and because they make the mirrors out of a material that can bend, they can get it into the right shape and keep it in the right shape. But then you have to have a computer analyze the data that's coming in all the time to adjust the mirrors to keep them in the right shape to allow for the varying atmosphere, and the dog managed to get in here. Come on, Steve. Hello, puppy.
Hello, Stu. Haven't seen Stu in a while.
Hello, puppy.
Oh, well. And while you're patting the dog, I do want to answer this earlier question from Mark Caesar. Have we seen the birth of a star that starts to shine? From my understanding, yes, we've actually seen a few. There have been a few occurrences where we have watched stars start to undergo fusion. It's not very common, but I know we've seen a few. What is more likely is that we tend to see a bunch of stars in various parts of their life cycle. So we can see them just before they start, just after they start, and then, as they're going, and then, of course, at the end.
Yeah.
One of the cool things that happened from, and this is why simulations, like running computer models, is still really, really, really useful, is that for a long time they were trying to model supernovae. And we knew they occur. We've seen them. They're very bright. They're hard to miss when they occur. We unfortunately haven't had one go off in this galaxy since we actually had the invention of the telescope. The last time it happened, I think, was a few years before the first telescope, back in the 1600s, if I remember correctly. And we're waiting for another one to occur, but they're so bright that we'll spot it. It outshines sometimes the bright center of a galaxy if it doesn't. So we know when they occur. But when we tried modeling them on the computer, so many times the model would fail to give you a supernova. The whole thing would just collapse and they'd just end up with nothing. And they kept going back going, okay, what are we doing wrong with the model? Why isn't it working? Until someone put their hand up and said, or it was actually probably a few people over the course of a while, but we simplify for the sake of story. It was like, what if this is actually happening? What if the real supernovas do fail? What if you don't always get the big, bright explosion that you see? And so they're like, okay, let's go watch and see if any stars blink out. We know what the rough life cycle of a star is, so we know how long they're going to last. Again, it's hard to tell if you just start observing a random star, but if you observe enough of them, then very, very soon statistically you can be like, okay, we know that they last X many years. Let's look at this many stars, and we know that after however many days we'll see one. And that's what they did. And exactly on cue, there was one star that just went boom, and it blinked out. And what had happened is it had collapsed into a black hole. The supernova had failed. Like it hadn't actually gone supernova, it had just collapsed. And it turns out that the computer models taught us something that was happening before we ever observed it. And it was from that we did. So computer modeling and doing all these weird corrections are very, very useful. And that's why you don't need to see every single bit before we have a good understanding of what's going on. Another thing to note with the infrared is that there's a lot. You can also see the red shift, so you can actually see how far away things are. But we will cover more of that. I think some of the later images are pretty good. Oh, actually, this is a good point. If the James Webb Space Telescope takes days of exposure to get these pics, past telescopes would have taken far longer to get them, and they wouldn't be as high resolution. That is true, but there is also something else that the James Webb has as a massive advantage to most other telescopes, including Hubble. Not only is it bigger, despite being 62% lighter than Hubble. If we have time, I'll get into how they managed to do that, because as a feat of engineering, this thing is impressive. But it sits in the shadow of the Earth. Its orbit is sitting in a place known as the Lagrange point. I think it's L5, if anyone is interested in math.
Or is it L2?
I think it's the one behind the Earth. So what it means is that it's just a stable point mathematically in the orbit where it will stay relative to the Earth and Sun, it will stay in the same place.
Yeah.
So as the Earth goes around the Sun, James Webb will forever be in our shadow, and it will just be circling kind of in that shadow. And that means that it is not getting all of the bright light from the sun. It is an infrared telescope, and it has to operate at below minus 200 degrees Celsius. If you go above that, it will fail to work. But the actual temperature is about minus 80 degrees. So yes, humans would not be very comfortable there because the universe does want to kill us off pretty easily if we move off the meter
tiny little thin strip we're allowed to live in. Yeah.
Yes, but that's why if you look at the James Webb, it's got those sails, all those foil-looking sails, and they're these amazing heat shields that are designed to take in heat and radiate it out. And the way that they've done them is it kind of reflects the light out of them. The way that they're angled, they look like they're just these folded aluminium sheets, but they're not. They're actually a fancy kind of tape that I've actually used in optics myself called Kapton tape. It's like sticky tape that is thermally resistant and will survive in space, but we use it in optics because you can heat things up, you can fire things at them, you can burn them with a laser. Well, you can hit them with a laser, you're not going to burn them. They're really, really useful. It's more expensive than regular tape, obviously, but you can actually buy it. It's off the shelf, but they have giant sheets of it that they've coated with. And I have to remember, no, the mirrors are beryllium. I think it's silver, but I have to double check. It's actually probably an alloy. I know what the mirrors are made of, but we'll get to those in a little bit. The heat shields, they are literally shields, but they take it down another 120 odd degrees, or well, it's a bit more than 120 degrees, but they take it down much colder so that the telescope itself can work. James Webb is observing about 1 photon per second. Now, if you go outside on a dark night, and let's say you're not right next to the city because light pollution, but you can even be in the metro area, it'll still work. Go look for the brightest star in the sky, assuming there's no clouds. You're getting about 1 million photons a second from that star. This thing is observing 1 photon per second. It is dark, and it is looking for parts of the universe that you would not see, even if the wavelengths were in the visible region. We can't see that. It's
Which is what goes back to that whole thing of our photos in the real color, is the fact that the loss of the ability to see those photons over distance is so great that we do have to interpret color back into things. Just observe, we would never get enough photons to get a true color image from anything that distant. It's not going to happen. So we have to interpret that from the data we get to get the color. Unfortunately, we've got nearer things that we can look at, that we can get ideas of what colors are meant to be, that we can then extrapolate out to the deeper universe. But in general, you can't. I mean, a good example of that is Jupiter is quite huge within our solar system, and it's this tiny little dot in the sky. And even if you get a reasonable telescope at home and look at Jupiter, unless you're going to take a long exposure photograph, you will not see any color. Just looking through the lens of the telescope, Jupiter will be a black and white image because you're not getting enough photons to discern any color. And it's the same for the James Webb Space Telescope. It's the only reason why we can discern any color is the amount of time we spend and how we filter the photons that come in.
Yeah, it's also kind of a false color image in that it's done this way for representing to us.
Yeah.
The actual image is not going to be analyzed by people looking at it like this. It'll be done through statistics, through software, and they'll be looking at the exact wavelengths that we're measuring. Spectroscopy is quite complicated. They'll be looking at the exact wavelengths that come through. I can chat a little bit more about that as we go on, but it's going to, how many days have you got for me to fully explain the basics of spectroscopy? I've spent the last...
Dust in space isn't like dust in your home. I mean, dust in your home is mostly skin cells and things like that.
It depends. That one can be true, can be false. It's one of those weird myths where it's like, yes, depends where you are, what sort of dust. But
yes, but I mean, that aside, my point is your dust in space is little bits of colorless grit, or it's larger amounts of a gas which only has any color at all because of its emission spectra, and that's the thing about this. Where we colorize it so that people who are looking at this stuff can get a better idea of what's where. as well. I mean, we colorize it for our purposes, not for the purposes of this is what it would look like. I mean, you could be standing within a light year of part of that, and you wouldn't be able to see it all anyway because it's 6 light years across. And even if standing within a light year of within a nebula like that, you may not, unless the nebula is well lit by something, you probably wouldn't see the nebula anyway because it'd be outside of our range of vision.
It depends. You'd probably pick up some of the dust depending on what elements it is. But yeah, it depends. Most of that dust is going to be hydrogen and helium. There's the old physics joke that the periodic table for physicists is kind of there's hydrogen and helium and everything else.
Yeah, pretty much.
Because it's 99% of the universe is hydrogen and helium. So they get about as far as lithium and then they just say the rest is metal. Because in terms of modeling the universe, it works just as well as trying to account for the rest.
When you hear an astrophysicist talk about the metallicity of a sun, it's how many elements it has other than hydrogen and helium in it.
Yeah. So, and that's one thing is that because I'm not an astronomer. When I hear metals from spectroscopy, I am thinking, okay, what generally transition metals have we got at the middle of the periodic table? But yeah, when I listen to a lot of my friends in astronomy, I'm like, no. They could be talking about carbon, for example. I mean, yes, it's not a metal, but to an astronomer, it may as well be. But spectroscopy is one thing that you can do very, very, very accurately. If you pick up a band, you can detect it. And I actually do have a picture later that comes back to this, so we'll do that. But I think I want to hit the next one. Just because, again, this is I could go for days on this. And again, anyone who has questions, feel free to put them in. I will have a go. I've seen one or two.
We're not getting into the electric universe, Mark Caesar.
I did see that. Lithium makes good batteries. But yeah, I could do a stream on how science documentaries have been lying about the Group 1 metals. I've seen one where they actually wired up a bathtub and used explosives instead of actually putting the chemicals in because they wanted a show. And it's just like, no, you don't use dynamite to mimic a chemical reaction that doesn't happen. Sorry, that's a stream. If people want to see it, put it in the comments. But for now, I want to go to this one. So
beautiful.
It is. The thing is, they look close to each other, but they're not. There's about 40 million light years between the galaxy on the left and the two that are colliding on the right. There is also another one down the bottom.
And the one down
won't
the bottom
talk too much about that.
Further away, because that would be a large elliptical, and it looks smaller than the other three galaxies. So
yes, but but it's the biggest one there. The smallest galaxy is actually the closest one, which is on the left there, and you can see that it's closer because you can actually start to make out detail. It looks a bit grainy, but that is actually because you can see the stars. Again, see how some of the closest stars around it have that nice kind of like the 5-point spread to their light. That's again that's just effects of the way we image it. But what's going on in this picture is you've got one galaxy just going on about its way, but the other two on the right there are two galaxies colliding with each other. And this is the mess as they start to intertwine, and the stars and the solar systems, and eventually the black holes in the center of them. I believe these two both have at least one each. But the really dense centers we're actually combining. In a human lifetime, we won't see much change to this image, but over time, you'll actually see them slowly go around each other. The dust will mingle, and they'll merge eventually into one. It looks chaotic.
About astronomy, though, is that we can see this, and this is captured at that point in time, but we have seen images of galaxy collisions in all of their various states, like near the end of the collision completing, and just before the galaxies get to each other, and as they're doing their dance, and you can see the two cores separate, but the outer edges of the galaxy are mostly pulled together. And so we've seen all these different stages, so we've got good models to work from to be able to create computer models to view it in our sort of time frames, because by looking around the universe, all these things, all these different stages are happening somewhere.
Yeah, one of my favorite analogies to that is that, say, an alien came to Earth and only had an hour to view the Earth, and they wanted to look at humans. They took a snapshot of Earth. You could still, without actually staying more than an hour, figure out the life cycle of a human. You could figure out how we're born. You could figure out what we look like as kids. You could see us grow up. You could see us grow old, and you can see us die. And you can do it in an hour because you've got so many people on this planet. You can get snapshots of every stage of that. And that's how we do this for a lot of things in astronomy. Our life, the length of the lifespan of a human is way too short to see much change on a galactic scale. We're here too short a time. But we can look around and see all the different stages. And every time you look out, we're looking back in time, which is the last image, but it is the best one for that. But we'll get to that.
I mean, an interesting aspect of that is for anyone looking out from a further galaxy, like further than Andromeda, or one of the ones in the outer part of our group, a larger group, any alien species looking back at the Milky Way and Andromeda, if they were seeing how it looks now to them, they'd be going, those two galaxies are colliding, because the very outer edges of Andromeda and the Milky Way are just starting that procedure.
That's one other thing I was going to point out. Yeah, we're on a collision course for the Andromeda galaxy, but we won't see we won't really notice the collision for what? It's quite a long time. We're talking
4 billion years for it to really get going. Nearly 4 billion years for it to really.
Yeah, where our sun will have. It probably won't have swallowed the Earth. It would have actually expanded out to roughly the radius of Mars, but the solar pressure that it's putting out from its radiation will blast us out of our orbit. So we won't actually get swallowed by it. We'll just get fried
pushed
by
out
it.
And burned
but we'll be long gone from this solar system by then. If we're still around, we might see it. But the thing is, from the point of view of our solar system, even after the full collision has occurred, we'd barely notice anything apart from a few new stars in the sky, because we're out on the edge and the distances between everything is so large. It actually
people go, all these stars are going to collide. No, they're not. They're not.
No, there's too much space between them.
Far apart that it's more like a case of two things merging than it is an actual collision. They're galactic mergers. They are not collisions, because they don't really collide. The only thing that might collide in the future is the two supermassive black holes, and that's not a guarantee,
the center, the most dense objects. And unless you're really close to that center, the collision isn't going to do much other than slowly. And again, you're not going to see it in a single lifetime.
The worst part about galactic collisions for any life in a galaxy is that the collisions of two galaxies tend to create pressure waves within the galaxy that pushes more of that dust and stuff together. So it creates an explosion of star generation, especially closer to the core. And that increases the radiation levels of the galaxy up. So depending on where you are, if you're a life form living in the galaxy, that can actually kill off life within a galaxy because of the extra levels of radiation.
Yeah, though we're right on one of the, we're on the extreme of one of the spiral arms. For us, as I said, we're not really going to notice the difference.
I mean, we're 30,000 light years, so we're a little over halfway out on a galaxy that's 50,000 light years across in radio.
I think we're far enough from what I remember my astronomy lecturers saying. We won't really notice the collision here.
No, we probably wouldn't.
We're
actually at a point where, depending on the angle that the collision happens between Andromeda and the Milky Way, you can actually have spiral arms break off and become satellite galaxies because of the shearing forces that happen. So like you can see in this image where the outer arms stretch and pull into different shapes, those sections can actually break apart and coalesce into little smaller globular clusters or spirals that, or little mini galaxies that orbit the larger galaxy. So it is possible that we could end up not actually in the finished merged galaxy, but in an orbiting mini galaxy. A small globulous thing, more like the small Magellanic Cloud.
And the other thing too is that we can actually model this very, very well. We've got pretty good models for exactly how we're going to collide. So it's not like physicists are like, oh no, we don't know what's going to happen. Oh, we're probably safe. We've got a really good idea.
These things are happening all the time. I mean, it's happening right now within our own galaxy. At the moment, the Milky Way is stripping the outer stars off both the large and small Magellanic Clouds. There's actually star streams that you can see joining between the two as the Milky Way is slowly eating those two satellite galaxies. Eating's not really the right term. Those stars are slowly being pulled in as the clouds orbit here. By the time the merger happens between Andromeda and the Milky Way, those two small galaxies probably won't exist on their own. They'll just be part of the larger Milky Way.
Yeah, by the end of the whole merger, I said the most thing will be, oh no, we've just got more stars in the galaxy. That'll be the biggest change from our point of view.
And then, of course, you've got the other big galaxy that's of the three big ones from our local group, which is the Triangulum galaxy. And that is probably not orbiting Andromeda, but it's close enough on that orbit that when the gravitational interference comes in from the Milky Way as well as the Milky Way and Andromeda collide, Triangulum will probably end up in a close, fairly reasonably close in terms of astronomical terms, orbit to the merged Milky Way Andromeda galaxy, which means that it'll become the next galaxy that this new super galaxy that is Andromeda and Milky Way mixed together, whatever they decide to, whatever it's going to be called at the time, because it won't be really up to us. It'll be up to people in the future.
If it's even humans, it could be a whole new.
We're probably 4 billion years. We won't be humans by then. Even if we're still around, we won't be humans. But then the Triangulum will end up like an orbiting galaxy around the outside this larger galaxy and slowly stripped apart. So the inner core galaxies of our local group will end up becoming one big galaxy, most likely a large elliptical, because there's enough mass there to end up being an elliptical galaxy.
Well, we've got things to look forward to if we can upload our consciousness to a computer that will survive everything. Yeah. But apart from that, I don't really fancy my odds of being around to see this as cool as it is. I do want to get a few questions because a few things have come up that are relevant to talking about. This is the first one. Seeker, this is actually really interesting. I do want to check that article out. I have a few of my colleagues actually work computationally with some of the telescopes in Hawaii. So I'll be curious to see if they had anything to do with it, or at least they know of the paper. So I'll ask them. But we've got some really good pictures of those. The reason those telescopes, along with some of the ones that you find in, say, the Andes, are so good is because they're higher up. They don't get as much atmospheric distortion as ones that would closer to the, I guess, cities or lower down. One of the things we're trying to do is correct for the atmosphere. That's what we were mentioning earlier with the mirrors. If we can do that, it means that we wouldn't have to put as many satellites in orbit to get these pictures. We can actually build a bigger telescope on the ground without losing out on the resolution that the atmosphere generally degrades from any image we try and get. And a few other points. Oh, this one here, this question. Have we seen the two supermassive black holes colliding? I don't think we've seen the supermassive black holes collide. Not that I'm aware of.
That's
although to get a supermassive black hole, I imagine you would actually probably have had some collisions. We've definitely seen black holes collide that are in about an order of magnitude bigger than our sun. So kind of the remnants of really large stars collide. Those were some of the first things LIGO picked up. They are working on
What we did get
developing.
from LIGO that is interesting is that what we haven't seen in our observation of black holes is we've seen stellar mass black holes, which are the black holes formed when stars collapse, and we've seen supermassive black holes at the center of galaxies. Well, not always. We have seen ones supermassive black holes that are not at the center of galaxies, but there have been rogue ones from after galaxy mergers and things like that, where one of the black holes has been thrown out instead of falling into the center. What we did see with LIGO was the merging of two stellar mass black holes to create an intermediate mass black holes, and we hadn't had any confirmation prior to that of intermediate mass black holes existing. So that was one. No, we knew they should exist. There's no reason why you shouldn't end up with intermediate. That you have to get to a supermassive black hole somehow, and you don't have stars large enough to collapse to form a supermassive black hole, so it has to form from mergers. But what we hadn't seen was it happen, which was a problem because the maths tended to show that in a two-body simulation, one of the black holes would throw the other one out if they were too different in size, and you would expect that they'd be different enough in size that so you wouldn't get enough mergers to make supermassive black holes, even in the time frame of how old the universe is. So it was a problem. Does this actually work? And we've seen it now with LIGO. We've seen two stellar mass black holes form intermediate mass black hole. I think that the two were about 20 times and 30 times the mass of the sun, and they formed one that was about 5 masses of a sun smaller than what the combined masses of the two black holes were, which you'd expect because you'd lose mass in the gravitational energy that happens when the black holes form actually causes them to lose mass.
These collisions release energy that is about 30, 40 orders of magnitude more than the largest nuclear device we could ever make.
And as mass is energy, you would actually expect a black hole to lose mass. So nothing can escape a black hole. It's not exactly true because
they actually radiate out, but you're safer next to a bigger black hole than a smaller one, because a bigger one, the radiation is spread out over such a much wider surface, or much larger surface, that you don't actually get fried. So if you want to fall into a black hole, because it doesn't kill you, and not the falling anyway,
from your perspective,
you do it near a big one
for a very long time.
You'd basically, as you fell in, everything you're doing, more or less, assuming the black hole's really big, you would stay normal. You'd still be able to operate if you had your spacecraft, and say you had a way to grow food and a way to refresh the air. All that's given. You'd be able to live out your life on this spacecraft, and all you would see is as you fall in towards the event horizon, the rest of the universe would start to speed up, like someone's hitting the fast forward button, and it's slowly getting faster, and everything would start going really quick around you, but you wouldn't really notice. The curious thing is what happens when other people watch you, because you will actually fall past that event horizon. And remember, light can still get in, so you can still see the rest of the universe, but light can't get out, so no one would see you. But people wouldn't actually see you fall in. They would see you get very close to the point that you'd fall in, then you would start to slow down, because as the rest of the universe speeds up for you, other way around, they would see you slow down. You'd start to go red, and then eventually shift out into the infrared, and eventually the radio part of the spectrum. So red shift is just relativity, yay.
And spread out along the surface of the black hole.
Yes, you would also get spread out. So as that happens, but people would see it very slowly. You'd basically, it's like the movie slow motion falling. You'd slow down, which is one of those things they haven't quite figured out. Is from the person who's falling's point of view, they would fall into the black hole, but from an external observer, you would never actually see them fall in. And they're trying to think if that's a contradiction or not. So we've got a little bit more to do, but we still have a reason in terms of trying to figure it out. But we have a pretty decent idea.
Short of actually being able to get close enough to a black hole to actually observe this. And bear in mind, it'll take a really long time to observe it, because the time dilation there is so extreme. You're probably talking magnitudes of time that is longer than the universe has actually existed.
Yeah, so it's not something I think we'll be able to answer practically. We'll just have to keep increasing our
probably.
understanding of physics about the universe and figure it out through the answers we get from that, through modeling, through the theories that we develop. Also, I do want to explain this one. I don't want to find out what it's like to be spaghetti. It's also one of the reasons I mentioned that you'd need to find a very big black hole, because if it's smaller, as you fall in, the actual term is spaghettification. Some people may have heard of it if you haven't. That's when the difference in gravity between your head and feet is so big that it stretches you and basically rips you to pieces. That's why a lot of black holes, if you watch the movie Interstellar, they actually did a proper modeling for a black hole, and there's even scientific papers published on it. They often have a ring of matter around them, a bit like the halos and the rings you'd see around Saturn, except a lot more intense. And that is because as objects get pulled towards them, planets won't stay, even whole planets won't stay together. They will kind of get stretched and ripped, and they'll end up being pulled into his flat disk as they go around it. It's just what happens when you have that sort of extreme levels of gravity.
We've actually taken pictures of that.
Yes, you can see it happening. We've had it happen all the time. And if you find any pictures of black holes cannibalizing things nearby or just before these sorts of collisions, then you will see that occurring. You'll see that as everything comes off, it gets pulled off and then it gets kind of flattened out. Because once I think the rush limit is where that'll occur. Once you go beyond that, it's kind of the point of no return. You're going to fall in, and generally you get spaghettification. So again, if you want to test out what it's like to fall into a black hole, find a big one.
You get rush limits with everything. I mean, Earth has a rush limit as well.
Yeah, so it's kind of the rush limit is where you'll actually fall in there. So it's basically, let's say you're on the moon, you're not going to fall towards the Earth because the moon's gravity will hold you. But as you move close to the Earth, eventually that'll switch over and you'll start to go in. If we're talking about stars, that limit is normally when it gets to the point where they're either getting closer or, well, generally they're getting closer or one's been fed mass, at which point will it actually start to pull matter off the other star. And it kind of happens a bit with black holes as well. You get to a point where now your own gravity is kind of overcome by being too close to the other object, and you'll start to feed in, lose mass to it. One of the other things, though, that your earlier part about what we have observed, one of the things that they spotted with LIGO, and this was the first time that one of the gravitational events was actually confirmed and also seen with other visible wavelengths. They first spotted it in the gamma rays, and then eventually, after going back through all of the telescope data, they actually found the event occurring with visible telescopes. Was the collision of two neutron stars, so not dense enough to make a black hole. And this is also one of the other gaps. We've spotted a lot of neutron stars, which are the densest objects in the sky. Basically, you could fit the mass of the sun in a small sphere that would fit over Sydney. It's about 50 kilometers across, yet it would contain the mass of our sun.
Yeah.
It's ridiculous scales that I don't even know how to explain. Though what happens is we've seen them collide. Well, we've seen plenty. Before we get to collision, we've seen plenty of them. We've seen various sizes, and we've seen various black holes, which are much heavier, because once you get beyond a certain density, you'll collapse into a black hole. But we hadn't really seen anything in the middle. And then when this collision occurred, the mass of the new object was finally in that gap. And it's just this weird kind of gap in the middle of things that we haven't spotted. And I think it's a bit like the black holes. There are certain regions of mass and certain types of stellar objects that we don't see because they're not easy to spot. Supermassive black hole, we spot those because they're so big that we can see everything else around them moving in a way that tells us they're there. And they tend to be in the middle of
galaxies as well, so...
Yeah, so we kind of know where to look. Yeah, and there's a lot of objects around them. Regular black holes and stars, they're really, really common. They're all over the place, so we generally can see them. And most of the time, it's the effects that they're having on the stuff around them. But I think there are these weird intermediates where it looks like they're just hard for us to spot because, unfortunately, that's the nature of the universe.
Well, generally speaking, a lot of the intermediates are caused by collisions. and they're not the effect of actual things collapsing into other things. So you end up with two neutron stars colliding or two black holes colliding. And the reality is that the system that got those two things close enough together that they could collide generally throws everything else out of the way that we could see them interact with. So they end up with this. We end up with this big thing that's sitting on its own somewhere, and because of that, we can't see it because neutron stars don't give off bugger all light. It's only the light of contraction and cooling. And black holes don't give off any light of their own unless they're accreting something, and you could see their accretion disks. So, yeah, you're not. If these things are on their own and not near anything else, we're not going to see them.
The actual collision does sometimes release light because right at the extremes, just outside the event horizon, you can actually get bursts of light coming out from the interactions, and that's how we picked up the two neutron stars colliding, because they would have formed a black hole. But right on the edges, they did throw a bunch of their mass off, and it released a bunch of radiation. And there was a slight delay between the visible light, the electromagnetic radiation, because it wasn't visible. We picked it up in gamma first. Did see the event in the visible, but the gamma burst that went with the collision actually arrived a split second before the gravitational wave, and they reckon that was. I think it was only a few seconds, but they reckon the difference was not that gravitational waves don't travel at a different speed, because they don't, not according to relativity, but it was the fact that the visible stuff had to come from further out. So it actually came from part of it that was a bit closer to us than the center where the collapse occurred. So it was that distance that did it. So we have again, it's one of these things that's really hard to spot, but when we do, we've seen enough of other things around the universe to have a good idea what's going on. But also talking about collisions, I think is the next one. This one. Just while we're still on that. This is two stars colliding. Or, well, not necessarily colliding, but the bigger one is cannibalizing the smaller one. This is also a good example of what we were talking about earlier. These are both infrared images. So again, not something you'd see. The one on the left, I believe, is near infrared, and then the one on the right, we're going longer wavelengths. Generally, longer wavelengths, you can see through more dust, so you can see further through things. You don't tend to get blocked by as much. And so in that first image on the left, you can't actually see the second star. You see one bright object in the middle with a dust cloud of stuff that's been thrown off this stellar event, whereas on the right, and this was one of the first times we actually saw it here, you can actually see both of those stars. So you can see that there's a blue kind of dot and then a red dot on the left. In the middle, those are the two stars that we're looking at. And just trying to get the name of these, because I don't remember them off the top of my head. Oh, okay. So I can't see the name, but anyway, back to what we're actually looking at. The dimmer star on the left, I believe, is the one that's thrown out all this dust. So it's kind of getting towards the end of its life. But the other one is a bit more dense and is starting to cannibalize it. But whilst this looks really, really cool, it's actually quite common. Most stars in the solar system are not, in the universe are not on their own. They reckon about 50% of all stars out there are part of a binary system, so there's two of them. We did actually observe a triple one, which is the gravitational mechanics you need to have three in anything close to a stable system is pretty hard to get. But this kind of two just orbiting each other for a very, very long time is very, very common. And then right at the end, this is often how you get stars orbiting black holes. One of them will kind of die and collapse, and then the other one still goes on for a little bit around it. But the weird thing is that as this goes on, they will change their size, and they'll also change what types of stars they are, because they'll start to cannibalize each other. If you get one that's a bit bigger and they get close enough, it'll rip the matter off the other one. And as it gets bigger, you get more fusion going on and it changes it.
It's also how you end up with type 1a supernova.
Yes, for a long time they didn't know what those were, and then they finally figured it out. anyone who's curious about it, the type that type of supernova is what's known as a standard candle. I think that's the right one, and that's how we figured out the distances to a lot of the more distant objects in the universe. If you ignore the redshift, because we actually needed to account for that, was we knew how bright the events were. They were always the same event. They had the same brightness, same image if you take a scan of the wavelengths. So based on how bright or dim they were, we could figure out how far away they are. It's like if you've got headlights on a road, if they're far away, it'll be dim. As it gets closer to you, they'll be brighter. And that's how we did it, because but they're known as a standard candle because we needed an event or a glowing object. It could be so many things that could do that, but we needed one that was always going to be the same brightness. And stars, their brightness will vary on a number of factors. Their size and their age will be two of the biggest ones, and we're not brilliant yet, although we're getting better at figuring out ages just by looking at a star. It's quite hard to do because we're looking at stuff going on in the core, and that's what's going to be the biggest determination of age, but we can't really see that.
The reason why type 1As are always exactly the same is because it's a neutron star and a standard star, where the star is orbiting, or the neutron star is orbiting the standard star, and the neutron star is pulling mass off of the normal star. As it pulls off mass, it reaches the Chandrasekhar limit. Is that right? Is that the right limit?
I think so. Yeah.
It's a Russian name, and I can't pronounce it.
I do actually have my notes from third year physics. Well, it wasn't my third year uni, but it's senior physics where we went through that. But back then, when we were talking about it, they hadn't figured out what it was. So it was actually, here's a bunch of theories. This is the most likely one, but these are also here. Here's the problems with them all. So when I was taught this, it was only a few years ago, maybe 5-6 years ago, they still hadn't figured out exactly what was going on. But I've still got those notes. But
so what happens is a neutron star absorbs this thing and then hits this limit of mass that it can maintain. At this point, it novas again. It throws off its outer layers in the type 1A supernova, but the star itself survives. The neutron star survives and starts doing it again. So these things happen in cycles. I think they can happen about 4 or 5 times before basically the star tears itself apart. But all of these, because they explode at this limit and always throw off the same amount of mass, mean that these explosions are always exactly the same level of brightness. So we can tell by how dim they appear to us here how exactly how far away they are, because we just measure the differences in brightness. It's so really fascinating that nature has something like this that is so standard. I mean, it makes sense when you look at how physics works, and how general relativity works, and how these things, that this would happen. But it's just fascinating from our point of view that you get.
Yeah, because you just don't expect something on when you see the sort of chaos, and I am using chaos in a very loose manner. I'm not using it in the formal physics sense, because when I'm saying chaotic here, I mean just because it's complex.
It
and
appears
there's so many different things going on that you don't expect anything to be really uniform. From a physics point of view, chaos actually refers to a simple system, but it's hard to predict. So a double pendulum or a 3 or more, or like a 3 gravitational body system, they're chaotic because they're hard to predict beyond initial conditions. But in this sense, but it deliberately avoids the word complex, because you can get things that seem complex, so it seem chaotic just because there's so many different parts, and that's more of how our universe operates. It seems so chaotic because there are so many things going on. But I just like this image. The main takeaway I want in terms of the way the telescope working is this is why we want to look at different wavelengths, because you can see very different things by just changing slightly. Going longer or going shorter, you can see that change. But I like the next image. Doesn't look as exciting, but it was very fascinating to me. One of the things that James Webb was pointed at was Jupiter. And this is not Jupiter. I'll get to what this is. And so the images from James Webb actually show Jupiter's rings brilliantly, because Jupiter has rings. All of the planets beyond Mars. So Jupiter, Saturn, all the way out to Neptune, Uranus. Oh, I should have just said them all there. Anyway, they all have rings. Saturn's are the youngest, and that's why they're the most impressive. At one point in the history of our solar system, Jupiter would have had a more impressive and larger ring system than Saturn. And I am really sad we didn't get to see that.
That would
Once
have been
upon a
awesome.
time. But unfortunately, rings around planets are not stable. I think the ones around Saturn are probably a few 100, 200 million years old. They're about that order of magnitude. So kind of formed when dinosaurs were walking around, more or less. I am going off the top of my head, so don't quote me on that one. But one of the things that they did want to do with James Webb was also try and look for exoplanets. It's part of the ongoing, amongst other things, like James Webb was designed to do a lot of things, as you can probably see already. We're looking at a lot of different pictures, but was also designed to try and pick up chemical signatures and detect, in the first place, exoplanets. This is what I do a lot more often. This is the sort of thing I look at for my work, is that I will see these sorts of graphs. You've got wavelength on the bottom, and then you've got, in this case, they're doing an amount of light in terms of parts per million. I don't normally do that. I'll use absorption or transmission, but it's a similar scale. And you're looking for absorption bands. You're looking for either where the light's coming through more or less, depending on exactly how you scale the axis. But every element, every molecule out there will have specific colors that it absorbs, unique colors to that element or molecule. Some things will be in too small a concentration to see. One of the problems with astronomy is that things are so far away that it gets really hard to spot things. This was the whole thing, if people remember back to, there might be life on Venus because they spotted phosphine. And one of the issues about it was they weren't sure about whether not only were they not sure about whether they'd seen phosphine, although I'm pretty sure now they were pretty safe to say that they had, but one of the problems was how much, because you're dealing with such like a paper thin layer on an object that's so far away. The actual resolution in the signals you get is very small. But if we remember how much trouble that caused just looking at Venus, which is closer to us than Mars, it's the closest stellar body to Earth, or closest planet anyway.
Depending on where they both are in their orbits.
Yes. At the minimum distance, Venus can be a lot closer. Yes, because it will vary. At the minimum distances that you can get between things, Venus does get closer to us. So you can imagine we can't see chemicals on Venus very well, but this one here is not looking at Jupiter, although if you have the chance, go look up the images that James Webb got of Jupiter, because it shows the rings brilliantly, because they're still there. And we were mentioning how hard it is to see even color on it. This is a Jupiter-like planet, exoplanet from another solar system. And they've managed to detect traces of water. So everywhere we see the H2O written, that's just an absorption band of water. As I said, everything absorbs unique colors. And by colors, I'm referring to the entire electromagnetic spectrum. So not just ones that we can see. Looking at these are in the infrared, because again, James Webb is infrared. You can see down the bottom, it's in microns. Normally I deal with nanometers, but 700 nanometers is the cutoff for the visible. So you can see there the first data point is 0.75. So looking at the scaling there, I think they actually start right at the edge of the visible spectrum. So this is just going beyond what we can see. And although water is clear to our eyes, it does absorb nicely a few wavelengths in the infrared. And you can see here that once they've done a best fit, which is the blue line, because the data, as you can see, all those white dots is quite noisy, you can actually see the water bands. So they've picked up water on a Jupiter-like planet very, very far away from us. I will have to check exactly how far away it is, and can try and do that in the meantime. But the reason I like this one is that it's my area. This is what I do for a living. So let me see if they can sound. Just quickly looking at the description NASA's put up, I don't see that they've given a distance. They just say it's a puffy gas giant planet orbiting a distant sun-like star. So this is basically another solar system's equivalent of Jupiter, but we've been able to detect a chemical on there. And I know it's hard to explain, but this is really, really cool. This is hard to see under the best of circumstance. Also, just to explain, this is a really common thing in science. You'll notice that all the white dots, whilst they're the data, they've got all these bars on them. Those are the error bars. And this is not we don't really know where the data is. You actually, the amount of times and that they have drilled into us and drilled into me, at least while I was doing my physics degree, about how you make these error bars. There's an art to it. It is not something you do just we think it's this. No, you go based on, okay, this detector, these measurements, this is exactly how we do it. We know what the error is. We're going to carry them over. There's maths behind it. You do it based on your equipment, based on the maths, and you calculate them. So the actual error bars are way, way more precise than a lot of the
1,100 light years, Matt.
Sorry?
1,100 light years away.
Oh, okay. Thanks for that. Yeah, so it's not that close to us, but considering how much trouble we've had looking at some of the closer objects, this is a pretty impressive graph.
Now that planet, that whilst it's a Jupiter, was slightly smaller than Jupiter. It is a hot Jupiter. So
yes,
it orbits a sunlight star every 3.4 days. So that's pretty close.
And okay, so at that orbital speed, there'll be a lot of tidal pulling, which will keep it warm. Yeah. Gravity can warm things up. It's the reason
not only
a lot
that,
of
it's really close to its star that's as hot as our sun. So
it's
going to be really hot anyway.
We're talking like a Jupiter that is a bit smaller than Jupiter, but similar scale, that is probably closer than Mercury to get that speed.
Which means that this solar system is a lot younger than ours, because otherwise most of that atmosphere would have been burned off. Or most of the atmosphere is burned off, and this Jupiter-sized planet used to be a lot bigger than what it is.
That's one of the other ones. And again, that's also why we won't probably be able to survive on this planet after 1 billion years. Although it'll take about 4 billion years for our star to die, our sun will eventually it'll go red giant and then it will collapse. It won't go supernova. It's too small.
It'll become a neutron star.
I think it'll actually be a white dwarf. I don't think they reckon. No, because you do need
to be a neutron.
No, it'll just basically, what will happen is it'll start to burn the last of its fuel. It'll get really, really big. It'll swallow Venus and Mercury up. It'll probably, the radiation will be so strong that it'll push Earth and Mars out of our orbit. So it'll actually physically blow us too far away to get swallowed, but it will expand roughly out to the orbit of Mars. Then it'll, right as it's burning the last of its fuel, going to every effort in the, I know I'm kind of giving it traits that doesn't have, but it will then burn the last of its fuel, and just like a car, it'll just conk out. And then all that mass, there's nothing pushing it out because there's no light, there's no energy being produced, no radiation that's pushing anything out. So it'll just, some of the material get blasted away, but it'll just conk out like a car and shrink
get thrown
down.
Out in what they used to call a planetary nebula, which is weird because they come from stars, so they're a star nebula. But that's where your star actually throws out its outer layers, and that actually happens in several stages because stars
I am oversimplifying. Oh, I am simplifying.
Stars don't actually slowly expand; they bounce. Because as they expand, they as the outer layers expand, it actually creates internal pressure in the core of the star. It's really weird. So the outer part of the star expands, but that actually creates inward pressure internally, and that can actually cause more nuclear generation because there's less fuel, obviously, now in the core. Because stars don't burn up all their fuel. Not all the hydrogen in our sun will get converted. It never burns it all up. But this bouncing effect where they grow larger and that creates more internal pressure, which sounds counterintuitive, but it's what happens. The throwing out on the outside, equal and opposite, the inner parts push in, actually causes a small bout of fusion. And because of that, the star stabilizes again and the outer bit shrinks back in. And then it does it again. And it slowly jumps itself out. We've actually watched this with Betelgeuse. Or that's not the correct way to pronounce Betelgeuse, but I've always said that. So, and we've actually seen it expand and then contract. And so the pressure waves isn't just a slow pressure wave as the star expands. It's multiple pressure waves that will slowly push the planets out. I mean, even Venus will get pushed slightly up from where it is, but eventually the expansion of the sun will catch up with it. Whereas for Earth and Mars, those multiple pressure waves from it expanding and contracting should push them far enough out that they don't get eaten up by the expanded star.
Yes. And I remember when my astronomy lecturer, when she was telling us about this, she was like, "Oh, good news! We won't get swallowed. We probably won't get swallowed by the sun because we'll get blasted so much radiation it'll push us away." And everybody was like, "Yay!" But we've got 4 billion years before that. But within 1 billion years, the radiation from the sun will get too intense for us, and it'll bake everything off the planet anyway. So we've had life on this planet has spent most of its time here. So we've had the planet's the solar system's about 4 billion years old. The sun's been burning for about that time. It's hard to tell exactly how long life has been on this planet. We know it's been around for 3.5 billion years. We have fossil record of microbial activity that far back. There is some evidence to suggest it was probably 3.8, which was a lot older than people expected because they thought that early part of the Earth's history known as the Hadean era, and if you think of Hades, the Greek equivalent of hell, was thought to be too climactic
because I mean you're talking about early bombardment periods.
So yeah, they thought too many things hitting the planet, but they reckon they might, even though they thought it was too harsh for life to form, it looks like possibly life may have started. The problem is we don't have any geology that goes back that far. Nothing lasts that long except a few small.
It's interesting how fast the outer surface of the planet cooled. In terms of the length of the solar system and that bombardment, the outer surface of Earth actually cooled reasonably quickly. I mean, not in our human terms, but in terms you're talking less than 1 billion years for the outer core of the planet to cool enough that you could actually have surface water because you needed the surface water to get the microbial life.
Yeah, and
so that's impressive.
Yeah. So they reckon we may. But anyway, about 3.8 billion years, maybe at a stretch, definitely 3.5. And as I said, we've got about 1 billion years left before the sun will unfortunately decide decide in quotes. Obviously, it's not a real decision, but to get rid of life in this solar system. Well, at least on here, the interesting thing is that when that happens, when it starts to happen, or at least towards the end, as it goes red giant, there might be enough radiation to have pools of liquid water ammonia mixes in places like Titan, around further away places where it's normally too cold.
And as we get closer to that 1 billion years, the temperature on Mars will increase to the point where we will get liquid water on the surface of Mars again. The downside to that is we may find that the extra radiation coming off the sun will be enough to strip it off the planet almost as soon as it forms, which is unfortunate. But if we're still around as a species, we may have the technology at that point to block some of the radiation that's coming not only to Earth, but also to Mars. I mean, there are ways you can do that with enough technology. There's also ways with enough technology you could also shift the Earth without waiting for the sun to do it. So that there are things. It sounds ridiculous when you say we could shift a planet, but technically you could. There is no reason why you
just need a bit of energy to do it. But anyway, that I think is a stream for all on its own about how really we save the Earth. In all honesty, trying to keep it back to James Webb,
that would be cool to have with Tessa, because it's almost like an alien.
So that would be We will have to organize that. But back to James Webb. This is the last image I want to have a look at, and this is my favorite. I've kept the best till last. This is James Webb's equivalent of the Hubble Deep Field image. We're looking at here
is because I wasn't sure if it was.
Yeah, so I know size-wise, we're looking at the equivalent of if you went out at night and held a grain of sand at arm's length. That is the size of the sky, the field every view that we're looking at here.
Yeah.
It is, if you went in, a set, we're talking about maybe 1 photon a second as opposed to 1 million from a star. The brightest star you'd see in the night sky with your own eyes. We're looking at a place that otherwise looks black. Hubble took 11 days to get its deep field image, if I remember correctly. This was still a few days, so it took a long time. It is, again, as I mentioned earlier, in the shadow of the Earth, so it can do that without much interruption. It's a very, very clever piece of engineering. But we're looking back in time to some of the earliest parts of the universe.
And
some of
every
these
single dot on that is a galaxy.
Yes, none.
There's very few
1 or 2 stars are
within that.
closer. There are still a few stars, but
Yeah.
all of those smaller dots, all of the smudges, even the ones that look like they've been bent circularly, those are galaxies, entire galaxies, and they all fit in a grain of sand at your arm's length. But we are looking back so far. If you look at the reddest dots towards the middle, so within the middle third of that image, you'll see a couple of really dull red spots. Some of those galaxies are more than 13 billion years old. I think the oldest they've spotted so far was about 700 million years after the Big Bang, after the
in the 70s, there was
initial inflation.
the estimate for the number of galaxies in the universe, and it was a few billion. Was the estimate that there was a few billion galaxies in the universe. The modern estimate is at least 100 trillion galaxies within our universe. That's a lot. That's several orders of magnitude larger than what we thought there was. And it's because of things like these deep field images where we've taken areas of the night sky that even with our Earth-based telescopes looked black. And we can see nothing but galaxies. And that's just for the visible universe. Over 100 trillion galaxies within our visible universe. The universe beyond that would also contain galaxies.
The universe is a damn big place. And this is one of the problems that we have in astronomy, is that trying to figure out the nature of the universe is not easy, because we are observing all of this from a tiny speck in the middle of nowhere on in part of a spiral arm galaxy that, when you actually map the universe out, we're nowhere near the center. We're not actually near the center of the universe. So we're looking from some outside little place.
Galaxy song.
Yeah. Watch the later version that Brian Cox and Tim Minchin did as well, because they actually went through the
corrected it.
Monty Python one and corrected them using our modern estimates.
Post that, Eric Idle and Brian Cox did it together as well.
I gotta go find that one.
Even more, that was actually where I got the 100 trillion galaxies in the visible universe from.
Yeah, you can see how our understanding has changed over the few decades between them. It's because they started with, you can see in the song the numbers they used. Because that was one thing that Monty Python did in that song, is they used the latest science at the time. They did it accurately. As silly as The Meaning of Life is, that song is probably the most scientifically accurate part of the movie. It was done well. It's just our understanding the universe has changed so much that we've had to modify the numbers. We've had to update the physics that was part of it. And we have a much better understanding.
Bit in the song where Eric Idle sings the original verse, and Brian corrects him, and Eric goes, "I can't sing that. It doesn't fit in the tune."
My favorite line is still the end of it, where it's like, "You better pray there's intelligent life somewhere up in space, because there's bugger all down here on Earth." I like that line. You gotta give them credit. But this image, we're looking back in time. This is a time walk back to probably about as close to the beginning of the local universe that we can see. And I just can't find an analogy to put that in perspective. I wish I could, but it's just an insane distance. But
it's awe-inspiring when you think about it. And if you've actually gone out and done any astronomy, even if it's only amateur astronomy, where you've got a few different size telescopes and you've gone and looked at nearby features, or you've tried to have a good look at the large or small Magellanic Clouds and that, and you can, and you see how hard it is just to do that, just to look at something that is relatively that close compared to this, and you see what we've been able to achieve with something like the James Webb Space Telescope or even Hubble before it. It's just mind-blowing, and it really puts your place in the universe in perspective, that the universe is just so vast.
If you haven't seen it before or heard it, go look. It's on YouTube. You can find it. Go listen to Carl Sagan's Pale Blue Dot speech, because I think so far that is the best, the most poetic and description of our place in the universe I've ever heard. And there might be some people who think that means that everything, it's like, no, that makes us seem too insignificant, but I don't think that's the case. Yes, it makes us realize just how big the universe is. So compared to the universe, everything that's happened on this planet is meaningless. But all I see from that is that means that it's more important that we look after each other here. The meaning that we're going to have is what we mean to other people, because the universe doesn't care about us. So it's up to us to care about each other. We're here.
And it's up to us to discover the universe for ourselves.
It's a big and impressive place. There's a lot we still need to figure out.
It's our universe. Why not be parochial about it and try and find out about it and get to know about it? Because it's our home as much as this planet is. So we should be looking at the bigger and the smaller picture of it all at the same time. We can't know us here if we don't know the bigger out there.
This is some of the redder galaxies in this image probably don't exist anymore. They're so old, particularly the oldest ones. And one thing I'll have to keep in mind is that StreamYards doesn't let me point very well to the pictures on here.
To be fair, most of these galaxies probably don't exist anymore. Most of them would have been involved in mergers and things like that. Because
and some of them may not exist at all, at least the way they're seen. And the reason we know how old they are is the redshifting. So I do want to cover that very, very briefly. One of my old lecturers did a post on Twitter. I think I retweeted it. If I haven't, I'll do it again. I'll go find it, where he actually puts a table out. So that compares when a scientist says something has X redshift, Z is the number. How old is that? And in terms of a percentage of how old the universe is, how much is it? So if it's like 50%, it means we're going back half the age of the universe. If it's 90-something%, then we've gone back 90% of the age. And most stellar bodies that we detect have a redshift. I think about half of them have a redshift of about 1, just under half of them. Most of them, I think like 90%, have a redshift under 3, because it's not a linear scale, it's exponential. But we're looking at things here that have about the maximum redshift we've ever spotted, which is close to 15. It's 0.3% or 0.1% of the universe that is that old that we can see. And one of the things, this is also how we know how old the universe is, or how we can double check that our estimates for the age of the universe are somewhat accurate. And by the way, when I say estimate, I mean that in a scientific point of view, and that it's not we took a guess and we think it's no. The science says
we're pretty sure about how they use the redshift.
It's an interpolation and extrapolation of data. It is not a guess in a colloquial sense. educated
In the same way,
scientific.
carbon dating gives us good evidence for how old the universe is because we can count the number of the decayed elements within a sample, and because we've got samples that overlap with each other all the way back to when we can count tree rings, so that we know that we've got accuracy across the solar plot. We have the same thing in looking at redshifted planets. We have seen standard candles out to a certain distance, and we've also seen standard candles close enough that we could use parallax to measure how far away they were. So we know that the standard candle measurement is correct. So at longer distances, we know that the standard candle gives us the right measurements, but we've seen standard candles out to a distance where we could measure the redshifts, which means that we can measure how accurate our redshift measurements are, so that we know these things all correlate and they come within a certain percentage of each other. Does that mean there's an error in measuring the really distant galaxies? Yeah, there is an error.
Yes, none of our equipment is perfect. In terms of the age of the
universe, it's minimal. Is what
and
it is, so.
The error bars, as I said, are pretty damn exact. They're based off a lot of factors that we know. It's like, okay, we know the equipment has a 0.2% variation in the light that it picks up. Okay, so when we do that, we'll add 0.2% into our error. Okay, this other input here has an error of 1%, and then you go through, you add them up, division. Depending on exactly what math is involved.
Yeah, you can
or
be,
it's like
in an object that is 13.2 billion light years away, you can be maybe 100 to 200, maybe 300,000 light years out in distance on average. Okay, that's the length of a galaxy, but you're talking about something that's billions of light years away.
As a percentage error, it is very, very, very small.
It is tiny.
The fact that we got the error down to less than 1%, I think, is an impressive feat in and of itself.
And it does in terms of how big the galaxy is. It's it's a tiny, tiny little distance in terms of the overall distance of the galaxy. In human terms, it's an enormous amount of error, but in terms of the universe, it's tiny. The really interesting thing, though, is that whilst we can view, we've seen galaxies out to about 13.4 billion light years now. We've seen the earliest galaxies. That's a lot earlier than we thought they had possibly could have formed in. But those galaxies, if they still existed now, which we don't know if they do, are now closer to 50 billion light years away from us because of the expansion of the universe. The universe,
and that is also what is part of the redshift. So I do want to bring that up because you said as the universe expands, the space between space expands. So what it does is the universe expanding stretches the light and helps with that redshift. But you can also reach the same answer based on like special relativity, general relativity, based on the fact that we are moving away and we're accelerating. So as we move away from the light, it arrives to us slower, but both of them give us the answer that we expect. So the light that we're picking up based on the redshift, it's not just the distance, but we can tell how long that light has been traveling for. This is not we looked at the standard candle and we assumed it was this. No, as you were mentioning, Jen, and as I'm trying to reinforce here, there are multiple factors that go into this.
Yeah.
We are pretty damn sure we know how old these things are. Yes, there is a small error bar on them, but in terms of our limited view of the universe from just the fact that we're watching it from a mote of dust suspended in a sunbeam, to quote Carl Sagan, we've done a damn good job. Even the furthest probes we've sent in terms of the actual distance of the universe that they've traveled is nothing.
And the interesting thing about that is with the Voyager probes, we can actually measure the redshift from the signals that the Voyager probes send back to us because we know where they are.
For now, they're about. Unfortunately, I know Voyager 1 is getting the point where I don't think we'll have much longer. Yeah, because it's too far away from the sun. The solar panels aren't picking up enough energy, and it does have a nuclear reactor on it, but even that's not going to last forever.
But we've actually been able to measure the redshift within our own galaxy of the expansion of
solar
the universe.
system.
solar system. Well, it's still within our own galaxy, but yes, I meant within our own solar system.
It's
within
beyond Pluto, but I don't think it's left our solar system, because our solar system does go beyond Pluto, but it has gone past.
To be fair, the expansion of the universe doesn't affect a galaxy as much as it does the space in between, because at these levels,
it only affects things where it's uniform
than the expansion. Yeah.
Yeah, if you have something
with an area where gravity is stronger than the expansion, so
yeah, and as soon as you have that unevenness that you get from a galaxy and having objects in it, you won't. That expansion doesn't really apply. It's a really complicated thing. There's also why we don't expand with the universe. We're too uneven. We're too heterogeneous for us to actually expand.
Too much gravity.
Yes, gravity is going to stop that. It's also why quantum mechanically we're always in one spot. We've been observed too many times for us to have that duality. Sorry, there are some people who like to think if you shrink a human down, but yeah, you can't do that. I think to get the scales of quantum mechanics, if you shrunk a human down that far, you get a mini black hole. But again, that's probably a stream for another time. How would you turn a person into a black hole? I could do the maths for you and figure out how wide it is. I remember one of my physics assignments, we had to figure out
release shrinking somebody down to that size.
I remember one of my physics assignments for astronomy was how big would a black hole need to be to heat your room? That was one of our questions. I loved it. It was a cool question, and it wasn't that difficult to do. It was in the order of less than a millimeter across.
That the Hawking radiation from it evaporating was enough to warm the room.
Yes,
but you'd be
and you had to then figure out how much. Yeah, and the way you would power it is you just occasionally drop stuff into it. So it's like, it's getting a bit chilly. Let me just throw some of my trash into the black hole.
You'd also have to have it big enough that it didn't instantly evaporate.
We kind of
that as well. So
yeah, we kind of ignored that one. We were like, let's ignore how fast the thing would evaporate. Let's just look at the amount of energy it's given off. We need this amount of radiation to warm the room, because they're one of the most efficient energy sources in the universe is dropping things into a gravitational well. But anyway, that's moving beyond James Webb.
Yeah.
But yeah, I think we're getting to the 90 minutes, so I'm going to finish up on at least me talking about it. I'll obviously, Jen, if you want to add anything, you can in a moment. But if anyone is still around, if you have any questions, feel free to ask. But yeah, we are heading towards the end, so now is the time if you have any questions about anything with James Webb or the items and the objects we've seen in the photos. But yeah, Jen, what are your thoughts towards this point?
About James Webb, I think it's brilliant. I wish that Hubble had done the near infrared instead of visible light. I think we missed a huge opportunity with Hubble by going with visible light rather than the near infrared. I understand why it was done, because pretty pictures sell the idea to the public. But for the aspect of the science of it, going that near infrared has just opened up so many more opportunities. I mean, we can actually, with James Webb, peer into the center of our own galaxy through the dust clouds. That's something that we haven't built any other telescopes to be able to do. We may actually be able to get even better pictures of our supermassive black holes with James Webb, because it is near infrared. Now, that's brilliant. And they can... it might be years before we actually see one, because they can take them as separate images at different times when James Webb isn't doing other science. Because it's in a stationary orbit at its Lagrange point, James Webb can point at wherever it wants in the sky for as long as it likes. It's brilliant.
And we'll get about
later, it's always going to be right.
Yeah, and we'll get about 10 years with James Webb. Unfortunately, after about 10 years, it will run out of fuel. And so, because it does need...
There's also issues that where it is, because it's in a Lagrange point, Lagrange points tend to attract a lot of dust and other things, so it'll also get its mirrors damaged over time as well, which will...
they've tried to design it so that it can correct. That was one thing they learnt from Hubble, because they accidentally made the lens too flat in Hubble, so it gave us blurry images, and they had to send someone up to fix it. Unfortunately, at this point, we cannot get to Hubble. Oh, sorry, get to James Webb. We can't send people up to fix it. It's not in a low Earth orbit. It's not orbiting the Earth in a sense because it's fixed at the Lagrange point. It is orbiting, but it's orbiting at the Lagrange point. I know that might seem like a very finicky distinction, but there is a big difference. So, but because it's so far away,
than it is to get to the moon.
Yeah,
and so it is that far away.
And that was one of the things is that when the shields were deploying, it deployed over several days. There was about 300 points of failure. So this thing is an amazing piece of engineering. They had to solve so many problems. James Webb absorbed about a quarter of NASA's budget for the better part of a decade. Mm-hmm. This is the biggest project NASA has worked on since landing on the moon. If you want to think about funding and time and effort, it's definitely the biggest thing since Hubble. This thing, and that the weird thing is they actually dropped it. It got delayed because they dropped and broke it in the warehouse when they were building it. They actually broke, I think, at least one of the mirrors because I don't know how you drop it because this thing is like 2 stories tall.
Not small.
It's not, but they dropped it. The individual hexagonal plates on the mirrors are about, I think they're 70 centimeters across there. When you put them, they're not much bigger than they're not much smaller than I am. And if you want to take the fact that it's a wider area, whereas humans are narrow, they're about the size of a person.
A mirror the size of one of those plates would make an awesome backyard telescope.
Yeah, and the thing is, not only can each of the plates themselves be moved to correct and align, and they actually did that deliberately so that it could basically deploy and align itself while it was out there without us having to pre-assemble it, which meant it could be packed smaller. It's also lighter than Hubble, despite being about 4 or 5 times the size of Hubble. It's 62% lighter because of the way they made it. It's a really good piece of engineering.
But it's about the size of a car, and James Webb's the size of a small truck.
So it's not small. Have a look at the videos of them making it, putting it together. This thing is pretty damn impressive. But the thing is, not only can each of those hexagonal plate mirrors move so that if one of them gets bumped, they can realign it, the actual shape of them can be warped and distorted a little bit. It's made out of, they're beryllium mirrors.
To adjust for atmospheric conditions within
they've used the same technology.
And they don't need that for atmosphere, but it does allow, like Matt was saying before, as the telescope ages and it gets damage to it, they can adjust the mirrors to adjust the optics to bring them back into focus. That's the idea. But I mean, they will eventually fail to themselves. Although
that's why I said they reckon about 10 years. Then the first thing to go is most likely the fuel, because once you're out of fuel, you can't align it, so we can't aim it at anything new. We can't keep it aimed at things. It doesn't need much fuel, and it's a very efficient fuel source. It's a solid, I think it's a hydrazine fuel, but I will have to double check that. Because once you're in orbit, you don't need much energy to move. There's nothing to resist. One of the other things is that
point in into a direction, and then it can use gyroscopes to stabilize itself in that position. So
one of the other things is they also design the heat shields so that if they do get a puncture hole in them, they're designed not to shred. It's actually taped in sections so that if you get a hole punched through, it won't split and rip. It'll ruin one grid, but that little grid space that they've done in the way they've made it means that you won't lose the rest of that shield. But eventually, yes, you'll probably punch enough holes through. So space is pretty dangerous. It's hard to keep things maintained. What they're hoping for is that within that 10-year lifespan that it's meant to have, that we will have the technology by the end of that decade to be able to send robots to it. And if we can do that, the robots can refuel it and can fix it. But unless we get that going, we've got 1 decade. But I mean, the amount you can do in a decade with one of these telescopes is impressive. Yeah. That's an insane amount of engineering. If people want to see me do a video on the engineering, let me know. There are some brilliant videos out there, so I'm probably better off finding a more niche area to do. But it is yeah, it's an
In
insane
all
piece of
honesty, within
engineering.
10 years, we could have it is conceivable we could have manned flight missions. So given that we're going back to that to Lagrange points, it is conceivable that we could
It
have the
is,
technology for that.
but I think what they're looking at is that in terms of safety and practicality, it is more likely to be a robot that will
Oh, it'd make what the
James
cool
Webb.
thing about a robot is if you develop a repair robot that you can send to James Webb, dock with James Webb, and you just leave it there. And then you've got
Yeah.
a robot you can set out to do repairs as you need it. And then when that robot fails, you send the next one.
Or if the robot can't stay on the telescope, you jettison it and let it just float off into space. No one's going to care. You can't do that with a person. You need to bring them back.
Point, so you could also, it's not going to leave the Lagrange point, so it could actually fly back to James Webb if it was needed later, if it still had fuel.
Yeah. And the thing is, yeah, you don't have to get it back to Earth because it will take a lot of energy to get back. And
no, you just keep it there. It's not going to go anywhere.
Yeah,
once it's stuck in that.
So yeah, I don't think we'll be sending people to fix it. They fixed Hubble with a person, but it's in orbit around Earth, so you can actually, yeah, that's something we've been able to do for ages, get people up there and back. And yes, we did technically do robots first, if Sputnik and its successors count as robots. I think they do. They're early, very simple ones, but we've been able to put things into orbit and get them back somewhat safely for a while. Relatively safely. It's more dangerous than driving a car. But it's
well, let's face it,
anything
you send into space is being strapped on the top of a big bomb.
Yes. The fuel in rockets has to be as efficient as possible, which means they need to burn as well as possible, which tends to lean them towards basically being explosives. So
well, something like hydrazine, it actually is more energy efficient in its explosions, in its way of burning and exploding, than something like C4. So that's the thing. You are
definitely more than gunpowder or gun cotton.
Yeah, you are literally riding on a big explosion, a controlled explosion, but a big explosion.
Damn well controlled, because I think we all know what happens when it's not. But yeah, there's a lot of problems with fixing it. But they were lucky because James Webb, there were so many things that could go wrong. Because not only did you have the 300 points of failure in the shields, you also had a whole bunch of failure points in the deployment of the actual mirrors. But fortunately, because the physicists, the astronomers, the engineers, because it's a whole collaborative effort. There's so many people with different expertise that went into making it, had learned from previous experience. We knew the sort of things that could go wrong. They knew how to fix them, or they spent lots of money to find ways to solve novel problems. One of them was, how do you make an efficient vacuum pump? Because they wanted a cooling system, and because the actual internal sensors that it uses to detect the light have to operate at a lower temperature than they could make with the heat shields. It has to operate cooler than the universe or the space is at that point. And so they basically did a standing wave in a tube and siphon the heat and out one end, and then obviously the other side it's going to be cooler. And so it was a very, very interesting way to make basically the world's most fancy fridge. But they had to be energy efficient.
Doing that in space, that's not easy. I mean, we think, okay, it's warmer here on Earth, we've got an atmosphere, but our atmosphere makes it easier to dissipate heat as well as trap heat. Whereas in space is not a good conductor of heat at all. So creating a heat pump system that can move heat from one location to another in space is really hard. I mean, it's one of those things in sci-fi movies that I really hate, is that a body goes flying off into space and they show it freezing. A human body would take that really. In fact, you can.
I think if you're lucky, you've got about 20 minutes in space before you'll die, and you'll basically you'll die of asphyxiation. There's no air, because you won't keep the air in your lungs either. The pressure in your lungs versus the vacuum of space will force all the air out. You won't be able to hold on.
And the fact that all all the fluids within your body will vaporize, actually gives off heat. So you'll actually get hotter first rather than colder.
Yes. Although I think the tension from your eyes and skin will still be enough to stop
Not
you.
to hold it, yeah.
Yeah, to
But
hold you together.
Yeah.
I know that no human has actually been exposed to the full vacuum of space and brought back, because unfortunately by the time that happens, something else has gone so
They've
horribly
done
wrong.
tests in simulators on organics,
And they have done it, I know, on monkeys. I think a chimpanzees, they have basically put in the vacuum of space, and they were able to resuscitate it after about 20 minutes. So they know that if you can survive for a little while, you'll pass out within a minute or two, because again, you won't have air. And you're probably going to get, like, most likely by that point have like permanent eye damage and potentially brain damage, because again, no oxygen.
Because the smaller blood vessels sort of explode.
But yeah, again, that's probably a chat for another one. So yeah, the vacuum of space.
I think we've actually had this chat before, but yes, you don't freeze in space because your body's a pretty good insulator, and space is not a good conductor of heat.
No, but that was one of the problems. They actually needed to put a cooling pump on James Webb. But it feeds the heat to its shields and that gets radiated away. So that's where it goes.
Which would actually take a long time to radiate away, because again, space isn't a good.
Mm-hmm. They had to design the shields very, like the actual angle of the shields. You'll notice they're slightly bowl shaped. The distances and angles for everything was calculated to get rid of as much heat as possible. Yeah, go look. There's some brilliant videos on the engineering behind it. They're definitely worth a watch, because this was not an easy thing. And it's the technology we got from this can probably be used to keep people safe in longer space travel, I reckon. Although on that note, we are at just over an hour and 45 minutes. So I am going to bring things to an end soon. But if there are any final questions, please ask them now, or you'll have to wait until the next stream I do.
Or catch us on Twitter.
Yes. Oh, yeah. Feel free to ask me stuff on Twitter. If I get enough questions on something, I'll do a stream on it. Jen.
Yeah.
What are your conclusions about James Webb / what have you got coming up?
I am excited to see what we're going to see over the next year or two, because what we're getting now is just snippets of what it can do. It's more or less them testing it. So what we're going to see with the longer exposures, when we're actually looking, I'm really interested to see the deep looks into the core of our galaxy, which we haven't really had that many good images of because of the dust in the way. And what we're going to see from other galaxies that especially within Laniakea, that's our the larger group supercluster we're in. It's going to be really fascinating what we can see over the next 5 to 10 years, and deep fields like this, where we can see back how far back were the earliest galaxies, because we keep finding that they go back closer and closer to the point of the Big Bang. The galaxies were started forming almost straight after. That is an amazing thing, because we thought the universe was too hot at some of these points for you to have large formations, and it appears that that's not necessarily the case, although these early galaxies would have been incredibly hot because things were still incredibly hot. It's amazing that this is, it's going to challenge some of the ideas, some of the preset ideas that I think we have about our universe, and I think that's brilliant. As far as what I got coming up, I am going to start doing a video series on language and evolution of languages, etc., and etymology of different words and stuff. Hopefully, I'll have something out in the next, if not this week, with the week after. So
I'll be looking forward to them.
Pre-recorded, obviously, and then I might do a couple of streams on language as well, especially I'd love to do a bit of the entomology on science languages, because it's not just about the Latin or the Greek. It's more interesting than that if we go into it. So that's could be something we discuss later, because it'd be interesting. But yeah.
Yes, well, I don't think I can add too much to what I've already said on James Webb, other than I am very curious to see, particularly in the next couple of months, because it will take probably another month, and then within 2 months, almost certainly, before the astronomers start to release their proper studies on these images, and that's when we're going to start to figure out all the actual details about what we're looking at. It's one thing for me to be able to point out and say, oh, look, it's this old, or it's, this is what we're looking at. It'll be another thing to actually go through the science, what that means. So stay tuned, because I'm actually, like, I know a few people who are working in that, so I'll try and keep abreast of what's going on, and I might do either streams or proper recorded videos on some of the studies that come out. As for what I've got coming up, I am going to resurrect the idea of doing a video series on what made World War I so deadly. Although I'm going to change tracks from what I said before, I'm going to do it based on weapons. So I'll go through the different, what we think of as the worst weapons in World War I. I'll go through the science of them and discuss whether they were the reason the war was so nasty. I do also have a stream coming up, although it probably won't be released for a while after I do it, where I'll be chatting about the chemistry behind why some of the World War I on the Navy side of things was so deadly, including why a number of ships blew up very easily. But that won't be on my channel. However, once I can confirm the exact details, I will let everybody know. But that'll be a nice video coming up. Another video I want, but will be quite a while, unfortunately, before I get to show people, because unfortunately I'm very busy, is I'm going to do scientists wear lab coats. I want to do a video where I go through and show what is it actually like to be a scientist. I'll hopefully be able to give people a bit of an insight as to what I do on a day-to-day basis. But I've got to clear a few things before I can make that work. At this stage, I'll be able to show a few video clips from things like some of the science shows I've done. I have some nice little hydrogen balloon detonations that I want to show as well. Apart from that, only thing I want to add is, as always, I've been almost a doctor. That's been Jen from Polymathic. And until next time, be like a proton. And because I actually need to make sure this is lined up properly, be like a proton and stay positive. Oh no, damn it, where's the outro? It's been a while since I've done one of these. I can't find it. Anyway, I am going to... it's in the other one. Anyway, I have found it now. Slight delay, but anyway. Till next time.